Welcome to the video about more enthalpy changes. So we're looking today at finding the enthalpy change of solution. If you look in the textbook chapter for this, it also covers the theoretical versus experimental lattice enthalpies, but we've already covered that in the previous video or in the lesson if you were in school. So our learning objectives for today are to calculate enthalpies of solution for ionic compounds using the lattice enthalpies and enthalpies of hydration. So first of all, we've got to think what happens when an ionic solid dissolves. So there's a picture that you've seen before a million times of an ionic solid where you've got the repeating pattern of positive and negative ions. And we know those bonds between those ions are very strong. So you've got that electrostatic force of attraction between the oppositely charged ions. So when it dissolves, it's a two-step process. So what happens is you've got the water molecules which are polarized. So as you know from your AS bonding, water molecules are polarized, so the hydrogens are delta plus and the oxygen is delta minus. So when you've got that lump of solid there, of your ionic solid, that water molecule, when it comes close to the ions on the edge of it, will form a bond with that ion because of the polarization of the water molecule. So if you've got an Na plus ion, like you've got at the top there, what happens is that becomes surrounded by the water molecules. And that's only a 2D representation. If you look at that, there'd be one in front of the screen and one behind the screen as well. And because sodium ion is positive, the negative parts, so the delta negative parts of the water molecule, in other words, the oxygen, will be the part of the water molecule that are attracted towards it. And that attraction is a bond. And when you're forming that bond, it releases energy. It's exothermic. And the same thing happens around the chloride ion, except there you've got the delta positive. The hydrogens will be facing in towards the ion. So when these water molecules form bonds with the ions, that then gives the energy to break apart the ionic lattice. So I've got the two steps written there, but they're not really in the right order. So it's got the ionic solid is broken apart and the ions become so far apart they're effectively gaseous. So if you could zoom in and look at your sodium chloride solution and you ignored the water molecules and just looked at the Na plus and the Cl minus, they'd be far apart and they'd be moving and they'd look very much like the particle diagram that we expect for gases. But they've had those gaseous ions have formed bonds with the water molecules and become surrounded by them. So that two-step process we can represent in an energy cycle. So if we think back to last year when we did Hesse cycles and we used this Hesse's law to calculate enthalpies that we didn't know, we can do the same thing with enthalpy of solutions. So if we don't know the enthalpy of solution, we can draw this Hesse cycle here. So if we take sodium chloride, which is a solid, so the enthalpy of solution, if you look back at your definitions, is where you take 1 mole of your ionic solid and you're dissolving that in water so that those ions become completely separated, so they're not interacting with each other anymore, and they become surrounded by water molecules, so they become aqueous. So the equation's written down there. So NaCl as a solid breaks apart to give Na plus, which is aqueous, plus Cl minus aqueous. So as I said on the previous slide, this is a two-step process. So you're breaking it apart into its gaseous ions, and we've seen when we did Born-Haber cycles that that's the lattice enthalpy of dissociation. And then if you take those gaseous ions and surround them by water, if you look back at your definitions, they're the enthalpies of hydration. So the enthalpy of hydration is for a specific ion. So you need two arrows there, one for the enthalpy of hydration of sodium plus, and one for the enthalpy of hydration of the chloride ion. So using that Hesse cycle, we can then write an expression for the enthalpy of solution, which is the enthalpy of solution is the lattice enthalpy of dissociation plus the sum of the enthalpies of hydration. Because if you remember, if we use Hesse's law, if we're going in the same direction as the arrow, we add it. So if we're going from NaCl as a solid towards the aqueous ions, we're going along that lattice enthalpy of dissociation arrow, so you add it, and then you're going along the enthalpies of hydration arrow, so you also add those. So you need to be careful here. So if you've got something like magnesium chloride where there's two chloride ions, then you're going to have to multiply the enthalpy of hydration of the chloride ion by 2 to get the right energy values. Sometimes in an exam question you might also be given the lattice enthalpy of formation rather than the lattice enthalpy of dissociation. And then you just change the sign of the enthalpy change because the lattice enthalpy of dissociation is the same value but the opposite sign of the lattice enthalpy of formation. So it's difficult to predict. So the enthalpy of solution we can have, it can either be exothermic or endothermic. It's normally a very small value. So if you think about when you dissolve things yourself, like sugar or salt at home, there's no discernible temperature change. So the value is normally quite small. But it's very difficult to predict if an enthalpy of solution is going to be exothermic or endothermic, because the same factors that affect the size of the lattice enthalpy, so the energy you need to put in to break apart the lattice, are the same factors that make the enthalpies of hydration large. So, for example, so it says there about high charge density increases both. So we talked about this in the previous video. So high charge on an ion is going to give you a high charge density. That's going to make your lattice enthalpy of dissociation high, but it's also going to make your enthalpy of hydration high. And if you think about the size of the ion as well, so a smaller ion is going to increase the lattice enthalpy because you're going to get a stronger attraction between the oppositely charged ions, but then you're also going to get a higher enthalpy of hydration as well.